Light travels so fast, it seems instantaneous. It takes light about 8 minutes to reach us from the sun. So when we look at the sun, we're seeing it as it was 8 minutes ago. Do we really see the sun? Are we living in the present? What is happening to time? Let's understand what's happening behind the scenes with the help of a scientist. Light travels at a speed of 300,000 kilometers per second. Suppose we fire a laser beam upwards and then turn on another laser beam downwards. They meet each other halfway in the middle. For the laser beams to cancel out each other, they should meet at exactly the same time. Here, there is no problem. We can assume that both the laser beams take exactly the same time to reach each other. So if one laser is turned on before the other, the beams will not cancel out. Suppose the laser is turned on at different times. As we keep increasing the distance, eventually the beams may start overlapping. However, there should be a time when they perfectly overlap. Let's increase the distance so much that the Earth itself is placed between them. The beams will still perfectly cancel each other out, if their timings are correct. Now let's bring the Earth closer to the beams. The lower beam will still reach earlier than the upper one, but now the Earth will cast a shadow. Let's move the Earth away again. The beams will still not align perfectly, but their difference will be the same as before. If we keep moving the Earth faster, the beams will perfectly align at exactly the same time. We're getting close to something amazing. Let's take this movement to extreme levels and approach the speed of light. Even if we approach the speed of light, the beams will still align perfectly. So what changes? Why does the speed of light not change? To answer these questions, we need to go back to basics. What is light? According to scientists, light is made of photons. Photons have no rest mass, which means they're massless. And according to Einstein's mass-energy equivalence, the mass of an object equals its energy multiplied by the square of the speed of light. Hence, photons have no energy. But wait, how can a photon, which has no mass or energy, travel at the speed of light? Well, this is where quantum mechanics steps in. According to quantum mechanics, photons have a wavelength and frequency. Their energy equals Planck's constant multiplied by frequency. And their momentum equals Planck's constant divided by the wavelength. Their speed is calculated by multiplying their wavelength by frequency. Hence, increasing the frequency increases the momentum but decreases the wavelength. So the energy and momentum of a photon are inversely proportional to its wavelength. Since photons have no mass, they can travel at the speed of light. But what determines the speed of light? Remember, nothing can travel faster than light. According to Einstein's theories, the speed of light in vacuum is exactly 299,792,458 meters per second. It's a universal constant. You might think that since the speed of light is a constant, something must be compensating for the decrease in wavelength, but that's not the case. Nothing compensates for this decrease. The speed of light just happens to be constant. This happens because the wavelength and frequency of photons in a vacuum are independent of the motion of the source or the observer. In other words, the frequency of light waves is constant throughout the universe. No matter where you are in the universe, what's your speed or the speed of the source, the frequency of light waves will be the same. Frequency is determined solely by the energy of the photon. This is why the speed of light is constant. Because of this property of light, it was difficult for scientists to understand why light waves do UNT produce a Doppler effect like sound waves do. Sound waves are longitudinal waves, meaning the particles of the medium vibrate parallel to the direction of wave propagation. But light waves are transverse waves, meaning the electric and magnetic fields oscillate perpendicular to the direction of propagation. This is why light waves do not produce a Doppler effect like sound waves. Because of this, Maxwell predicted that light waves should travel at different speeds in different inertial frames of reference. But experimental observations showed that the speed of light is the same everywhere. The constancy of the speed of light led to the development of Einstein's special relativity. But how does it affect everyday life? Although light is a constant in our everyday lives, it doesn't seem constant to us because we are slow compared to it. A ray of light takes about 8 minutes to reach us from the sun, but it takes only 0.12 milliseconds for it to go around the Earth. Therefore, when dealing with everyday objects, we don't notice the constancy of light. How did scientists prove that the speed of light is constant? In 1887, American physicists Albert Michelson and Edward Morley conducted an experiment to determine if the speed of light is constant. They fired a beam of light into an apparatus that split it into two parts and recombined them. They expected that the interference pattern of the light waves would shift. Since the Earth rotates and moves around the sun, they thought that the speed of light would be affected by the motion of the Earth, but they were wrong. The experiment proved that the speed of light is constant. The fact that the speed of light is constant in all inertial frames of reference revolutionized our understanding of the universe. It paved the way for Einstein's special relativity and changed the way we think about space and time. One of the main pillars of special relativity is the idea that the speed of light is the same for all observers. This means that no matter how fast you are moving, whether you're sitting still or flying through space at half the speed of light, you will always measure light traveling at the same speed. This seems counterintuitive because in our everyday experiences, speeds are relative. If, for example, you throw a ball while standing still, it will move away from you at a certain speed. But if you throw the same ball while running, it will appear to move away from you even faster, because in that case, you are adding your speed of running to the speed of the ball. However, this does not apply to light. No matter how fast you move, if you measure the speed of light, it will always be the same. Approximately 299,792,458 meters per second. How does this happen? That must be some sort of compensation for the reduced wavelength. Otherwise, how can it be possible for the speed of light to remain constant? Well, there is no compensation. The speed of light just happens to be constant. This happens because the wavelength and frequency of photons in a vacuum are independent of the motion of the source or the observer. In other words, the frequency of light waves is constant throughout the universe. It doesn't matter where you are in the universe. What's your speed or the speed of the source? The frequency of light waves will be the same. Frequency is determined solely by the energy of the photon. This is why the speed of light is constant. The constancy of the speed of light is one of the fundamental principles of special relativity. It is the basis for many of the counterintuitive phenomena that occur at high speeds, such as time dilation and length contraction. For example, if you were traveling at half the speed of light and you shone a flashlight in front of you, the light would appear to be traveling away from you at the full speed of light. Even though you are already moving at half the speed of light, this may seem impossible. But it is possible because the speed of light is constant. The constancy of the speed of light has profound implications for our understanding of the universe. It tells us that space and time are intertwined in a four-dimensional fabric called spacetime, and that the passage of time is relative. It also tells us that the universe has a speed limit, and that nothing can travel faster than light. Understanding the constancy of the speed of light is crucial for comprehending the nature of our universe and the laws that govern it. It is a cornerstone of modern physics and has led to some of the most important discoveries of the 20th century. Whether you are a student learning about physics for the first time or a scientist working on the cutting edge of research, the constancy of the speed of light is a concept that you must master to unlock the secrets of the cosmos. That's all for today. See you next time.